Hello, this is Greg Risteman from Olympus. I'd like to welcome everyone today to this webinar titled Confidence You Can See, Introducing the OmniScan X3 PAUT TFM Flaw Detector. In this webinar, you will learn everything you should know about the new OmniScan X3 Portable Phased Array and TFM Flaw Detector. You will learn about the features that define its innovative TFM, how it improves phased array inspection, and why it's reliable and easier to use. Our presenter today is Tommy Bourgeois. Tommy has worked for Olympus for over 19 years and is currently a senior product manager for the OmniScan product line. Throughout his career, he's contributed to the development of probes, applications, the improvement of existing products, and has performed numerous trainings. This informational webinar should last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we don't get to your questions during the webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Tommy. Tommy, take it away.
All right, thank you very much, Greg. Welcome, everybody. Thank you for signing up and watching this webinar. This is going to be an overview of the OmniScan X3, more or less of the demonstration of the product through the webinar. This is what you're about to see. This will be quite a general overview. We will not go in depth. We will not go in details. There is a series of webinars that was advertised. You probably saw that as you registered for this webinar. And more explanations, more technical details will be given on each webinar going forward. Again, this one is an overview. So for the sake of keeping the time on this webinar, I will touch on these subjects briefly, but at least it should give you a good overview of what the OmniScan X3 is capable of, what it has for main features, main innovations, and hopefully you'll enjoy this. So I apologize. I'll be coughing a little bit, but we'll try to make that as easy as possible for you. All right, starting with the product, I need to speak shortly about the actual enclosure, the actual box of this portable OmniScan. So a great way to introduce that is going through the main phases of this enclosure, starting with the top. So what's new? We have two UT channels, PR pulsar receiver. That means our 4 connectors, P1R1, P2R2. Basically, one typical usage is you can get right off the top, you can get 2 TOFD channels, time of flight diffraction channels. Next, LEMO connector. We kept the same pin out, the same connector as on the MH2 and SX. So no compatibility problem there. There's an alarm output, as should be. And there's the same quick connect and quick connect phase array connector, which you can remove. You can remove the lip just like on the MH2 and convert it to be compatible with older probes. Now, if you notice, all of it is mounted on top, which is really the best place to put connectors. So instead of looking for connectors on the side like MH2 would do, now they're all on the top. So extensions will fit the top as well, or splitters rather, and just makes it very convenient. All right, moving on. The front view. Obviously, the instrument is a touch screen. It's in this embodiment. It's a resistive touch screen, a little bit over 10 inches. Really sturdy, really reliable under harsh conditions. With rain, for instance, it really works well. So we're quite proud of this enclosure and the way this casing is robust and resist all the harshest environment. So to keep the simplicity, we have used a more of an SX style. Those familiar with OmniScan SX will be familiar with a limited number of buttons that are quite optimized for what you're doing the most. We also optimize a user interface, which will be presented in later slides. But one of the things I want to draw your attention on is the knob. Well, what can be said about a knob on a PowerPoint like this is the knob, first of all, we did make some more room to be accessible. Plus, the knob has been made a little bit easier to use, even further easier to use, just because of its inertia and the way it feels in the interface. So you can rotate it and really have a good impression as you dial in the different numbers. The knob works with pretty much everything in the interface, making adjustments on the spot very convenient, or analysis through using the instrument. All right, left view, we do have USB 3 now, and a bunch of other connectors. Ethernet SD card slot is still there. HDMI output is actually what I will use repeatedly today throughout this demonstration. I do have a capture device that's connected to my HDMI port, and I will feed the HDMI display through this presentation. So you will be able to see live streams in a few minutes. All right, on the other side, we do have actually there's a hidden compartment. If you remove that top battery, you can access you can pull a tab here and insert a wireless dongle. For regulatory purposes, we chose to sell it separately. There's a standard model, there's for various regions. So you insert this, you take the pull tab where it belongs and put it back there, and it becomes a connected instrument. Now there are two batteries, two slots for two batteries, and they are the same batteries as with Image2 or OmniScan S6. So the batteries you already own will also work with the OmniScan X3. All right. Next, this is just a quick photo with the stand open, showing various positions using the backstand. All right. So I suppose that when you registered at the webinar, you wanted to see screens. What does it have for software features? So here we go. We're going to have a deck of slides and a mixture of demonstrations to illustrate the various features and benefits of the OmniScan X3. The number one reason to have an OmniScan X3 is its innovative TFM. So what does why is it so innovative? So what have we put inside? Well, one of the first obvious features to notice is its live TFM envelope, or live envelope processing, something we introduced with the OmniScan X3. Sorry for the coughing. It's quite a unique feature that basically provides just a better image. That's the actual benefit from it, is holds around in a live manner, and smaller defects are easier to interpret from the more crisp image. So, and now before I go into a demonstration and more explanations, I'm expecting that many of you will ask, all right, so how does it work? What's this process? Is it a filter? Is it something else? So here's the explanation, the written portion. So I'll go through that very briefly. I have a slide after that has an actual image, so it might be easier to explain it. So to obtain the envelope of a one-dimensional signal, such as an elementary A-scan, the complete analytical signal is needed. This analytical signal comprises a real and an imaginary part. So the acquired signal, or the standard A-scan, represents the real part of the analytic signal. The imaginary part must be computed from the real signal, and this is done using the Hilbert transform. Those familiar with TFM will know about the Hilbert transform. In simple terms, the Hilbert transform adds a phase offset of pi divided by 2 to the real signal. So the signal envelope corresponds to the norm of the analytical signal. All right. So if that wasn't too clear, also have a simpler pictured version of the same explanation. Same explanation, but with images. So number one is compute the imaginary signals. That's the real component that is normally what you get with an A scan on a typical flaw detector. What we do is we compute the imaginary signal from it. Now, if you look closely, you'll see that the signals are not exactly the same and not exactly the same phase. So we do combine the two, compute the envelope from that analytic signal, and extract the norm, and that becomes our envelope signal. Again, more explanations will be given in subsequent webinar, and I hope this is enough for you just to have an idea of what this is. I will not go further in details. I hope you signed up for the other webinars. So, in terms of benefits, I went briefly on that. What does it get you? It gets you a simplified representation. So instead of having a starfish representation, just like this one is with the envelope off, when the envelope is on, this is an image from a sidereal hole, by the way, with a bit of zooming into it, so it looks elongated. But instead of looking like a starfish representation, we do have holes that look round, which just makes it easier on the eye. The other advantage is actually a bit more subtle, but once you know how to tune all the parameters, you can actually get more speed with the envelope on. So why is that? Because the envelope enables a lower density grid, therefore higher productivity for the instrument, having less basically data to display in real time. And the reason why we can do that is because it's possible to preserve the same amplitude fidelity, which again is a term that will be more explained in the subsequent webinars. But the amplitude fidelity is found in the codes that are active, and basically it's possible to use a much coarser grid with the envelope on than without it. So here's a quick example that I will demonstrate. It's a 40 mm thick carbon steel demo block. I will show you those live signals in a few minutes. And I'm using an angle beam, basically 5L32, 832 weld series probe, and I'm using a zone of 55 millimeters by 40 deep in TT direct imaging path, which is transverse mode. Now, with the envelope off, with those settings, I get a PRF of just above 12 hertz, which is not that high, with an amplitude fidelity of almost 2.0. Well, maybe I could have fine-tuned that to have 2.0 dB, but anyway, for the example, so that's sufficient. And that gets us a resolution of 0.08 millimeter per pixel, which is translating into just below 700 by 500 grid. Now with envelope on, with my amplitude fidelity tuned at 2 dB, I get an actual higher PRF because I can use a coarser grid. Instead of 0.08, I'm using 0.17, and I'm having basically cleaner signals with faster PRF. I'm winning on the two fronts. All right. So if that portion wasn't too clear, I will switch to the live stream and show you the effect of the envelope in a live fashion. I will really share my live feed from my X3 right now. Hopefully you can see it. And please bear with us. It's a little choppy over the internet. The instrument is definitely very fluid, but when it goes through internet and depending on your location, you might have poor refresh rates. So I'll try to go a little bit slower in my demo to make sure that all the screens have the time to reach your computer, basically. All right. So what I have on this display is the same 40 millimeter demo block. Those are sidereal holes. I'll show you some more real light defects later on, but I'll start with sidereal holes. It's easier to start from that. So what I'd like to show you is, or bring your attention to, all right, so let me prove it's live. It's live here. So I have stacked sidereal holes. I have sidereal holes at the bottom, and I have a series of them. It's just a simple demo block, not a calibration block, just for the show. So what I have here is my acquisition rate of 11 to 12 hertz. My grid is tuned, so I have an amplitude fidelity of 2 dB. All right, I'm code compliant. And then basically the number of points per lambda L is just below 8, 7.9. I'm just fine. And this is using a single group in LL mode, basically a direct imaging, longitudinal, just like a pulse echo 0 degree would do. The probe I'm using right now is a 5L64 NW1, or in more common language, it's the near wall probe with 5 megahertz, 64 elements. I'm using all 64. And I'm using a wedge, which is a 0 degree, 20 millimeter thick on my demo block right now. So that's my setup. All right. So right now the envelope is off. I will go and display the effect of it, of the envelope turning on. So I will just pin this menu on the side. All right. So you can see those flaws in the, let's say, envelope off. Whoops. I will activate envelope, and now holes become round suddenly. However, the PRF drops, or just dropped. All right, so it half. It was just below 12. Now it's only 6. It's pretty low. So what I'm going to do is I'm going to optimize my amplitude fidelity by increasing my grid size or decreasing the resolution in order to have a more coarser resolution while preserving the nice image, but hopefully get something out of it. So that's exactly what I'm going to do. So I switch to the different parameters. And by the way, I will get back at explaining the various tricks of the interface a little bit later on, right? I'm really focused on showing you the effect of this envelope. So what I'm going to do is change my grid. Right now it's 0.15 millimeters. I'm going to more or less double it, use a grid that's about twice the size. So when it's finished computing, watch these two numbers here. Now my amplitude fidelity is just below 2 dB. I'm pretty much optimized. My number of points per lambda L longitudinal is 3.8, just perfect. And my acquisition rate has gone up. It was nearly 12 before. Now it's actually higher than before. And I have the live envelope on. So what I can do is kind of prove that by moving the probe around. Okay. And even with those little holes being close to one another, I can have some decent separation between them. So this is with a zoom factor. Okay. All right. Okay, that was the first part of my demo. I'm going to load a file now. I want to show you HTHA, high temperature hydrogen attack. So I have a sample data file from a HTHA sample that has early stage HTHA, which is pretty much the most difficult to detect or image anyway. So I'll be showing this is obviously it's a live feed from my instrument, but it's a recorded file. So the only thing I'm doing is I'm playing the file back on my instrument. So this is it. On the left side, what you see is the side view. It's like a merge volumetric side view displaying the maximum amplitude on the side against time or distance. And here I have the end view. So what I'll do is I'll press this button here, which is called the scan. Okay, it's the scan position. So it's actually a button that allows me to review the data. Okay, so I want to move my cursor here where the flaws are a little bit more elusive and harder to see, and just show you how well the X3 represents each of them one by one. And this is with the envelope on. So I'm purposely scrolling very slowly so you can hopefully get to see through the distance and the internet each of these flaws being refreshed one by one. Okay. Now, let's go back to the PowerPoint presentation. There's a second part to this innovative TFM message here. Another aspect that defines the OmniScan X3 as having innovative TFM is it can do multi-mode TFM. And for this example, we're using the same probe, and I'm using up to 4 modes because the OmniScan can do it. So why having 4 modes, or why having more than one? As TFM will exhibit different sensitivity to, obviously depending on the different modes, but also the different type of defects, and also where the defects are located or their characteristics. Having more than one view really comes handy to look into the various characteristics of the defect. On this example, I do have a couple direct imaging paths, the 4T and the 2T, showing the tip diffraction. I have a track profiler here, which happens to be a 3T on this example. And I'll be quite honest, at the moment of taking the screenshot, I don't think this one was actually doing anything, but I'll be showing you a much better screenshot as we progress in the demo. Just before I hit the actual demonstration screen on the X3, let me show you a quick example of TFM with multi-mode applied to COD, circumferential OD, such as with ERW, weld scanning. And this is with the envelope on. Right now I have only 2 groups, but you can have up to 4 again, and it just shows a fantastic representation of a mid-wall volumetric defect here. Okay. Another aspect that defines the OmniScan X3, quite a unique feature at the moment, is that it's called AIM. AIM stands for Acoustic Influence Mapping. You could say Acoustic Influence Modeling would be quite equivalent. So what it does really is it's an onboard simulator that allows you to visualize the coverage of your wave sets or TFM modes. So why would you do that? So you can see actually where the sensitivity stops. You can adjust your scan plan accordingly. So it's really an onboard simulator that gets that does respond to the various characteristics of your setup and displays the almost instant simulation. And it's time to show you that. So I'm going to switch back to my display. All right. And as I was talking, I just loaded another setup, which this one is prepared to have 4 TFM modes simultaneously. All right. So what I'm having here, I'm using of course, you see the string, but you don't see the plate. Let me go through the setup a little bit. So I'm going to go back to scan plan and show you what type of configuration we have. First of all, it's a 24 mm, just below 1 inch thick plate. Okay, it's a single V weld. If we look at the weld parameters, and I'm inspecting that with a 5L832 probe. It's a weld series probe with the corresponding shear wave wedge angle beam. It's a N55S, and I'm using it in TFM mode with 4 groups. So when I go to groups, you can see the 4 groups here at the top. You have 4T, 2T, 5T, and 3T. So those are labels. I chose those names in function of the wave set that is being chosen. And instead of typing TTTT, well, becomes a bit annoying after a while. I just punched in 4T, 2T, 5T, and so on. So you can actually name your groups like you want in a very easy way. Just have to press the group name here, and it brings you to a group, a naming menu. Okay, so you can either accept or change it. So right now I'm going to not change it. This setup is pretty finished. All right. So talking about the AIM, the acoustic influence mapping. Let's say I select this mode. Right now I'm on pulse echo TT, so direct imaging 4T. Let's say I want to change to LL. So I just press the LL button. So you can see the little circle there. So the OmniScan X3 is recalculating everything in the AIM display based on the wedge, based on the probe, based on frequency, parameters, part, velocity, thickness, the defects also. So it's, and not to forget the wave set. So quite all parameters are taken into account to have a very much very realistic simulation. By the way, we also have record of associating simulation with actual flaws, so we made sure that it does represent the reality. It's not only a simulated unverified. This has been verified with laboratory experimentation. So how does it work? The AIM basically takes each pixel of that grid one by one and simulates what if I had a side drill hole of 1 millimeter in diameter. This is the actual defect that it's taking, that it's using for doing the simulation. It's considering when the switch here is set to spherical, it considers 1 millimeter side drill hole, 1 millimeter in diameter, and assumes it would be placed here, and then calculates the return the sensitivity or amplitude, and then it computes the same for the next pixel, and so on. So the simulator computes all of the pixels in the modeling here, and basically finds the maximum and says the maximum becomes 0 dB. So all the colors become reference to 0 dB, being the maximum sensitivity of that given flaw you would get with that specific configuration. Now, this scale is graduated in dB, so from 0, -2, 4, 6, and so on, up down to -14 and less than that. So I like the yellow color because it quite coincides with -6. So it gives you an idea that the best sensitive zone for that configuration would be in the red-orange area, and at the yellow boundary you would have -6 dB of sensitivity. If you had the same flaw, basically if you had the same flaw here and there, you would notice a 6 dB difference just from the actual sensitive zone. Now I'm going to go back to the 4T. So for more details on the AIM, again, subsequent webinars will be a little bit more explicit on that. So I want to show you quickly the different parameters I use. So on that 4T, since it's quite well covering the haze and the bevel, I had the zone set at -30 up to 5. And the depth on the depth axis, it's for practical reason, it's almost 0 down to the maximum thickness. So I will show you the different modes. So that was 4T. Let's go to the 2T. So you can see the effect of, same probe, same part, but just changing the wave set changes the response drastically. Now let's go with 5T. 5T is a self-tandem. It's not a pulse echo mode. It's a little bit more complicated path. It accounts for 5 different, distinct legs during the ultrasound travel, or the expected ultrasound travel, I would say. So that's the map for 5T. I also have for 3T. So you can see it's quite fast to change the simulation. From one mode to another, the AIM gets generated very quickly. And that's being generated each time. It's not a pre-recorded or anything. It really gets simulated real time depending on your current parameters. So, all right, enough about the AIM for now. Let's exit this menu, and I will show you some live signals using that specific configuration. So for the sake of this demonstration, I will be scanning in time-based. There are 3 defects on my plate. There's an OD flaw at the toe. That's pretty much the one I'm looking at right now. There's a lack of fusion, and there's also a center line, root track. So I have one probe. My two, the different defects are on the 2 sides. So I'll be showing you the various displays the OmniScan has to view those defects. So first of all, this is toe track. Now I'm switching sides to show you the lack of fusion, which is easily seen on the 40. And how do I know it's 40? Actually, if I click on the top left group, you may notice there's a small circle here. It's a green circle. It indicates the current group. Okay, so this is my current group, and I can see the label next to the top here. It says 40. So I know this is 40. So if I select on the next, so top right is 2T. Down here, bottom left is 5T, and I have bottom right is the 3T. So in order from top to bottom, left to right, I have 4T, 2T, 5T, 3T. So the 2 top ones are the direct imaging, pulse echo. The 2 bottom ones are the self-tandem modes. Okay, that's the lack of fusion, and I'm trying to locate this root track. Just need some couplant here. All right, there it is. This one is quite shallow, so it's not a very deep root track, but still shows quite different responses depending on the actual mode. So what I'll do is I'll switch display. That was multiple layout with end view only. Let's go to basically a side view and end view showing the different displays. Okay. All right, so sorry, just a quick refresh here. All right. Okay. All right, so this is, I'm going to reset my display. I'll do a quick, time-based scan. My encoder's not connected here. That was a lack of fusion. Now I'm about to hit that root track, and now just switch sides briefly to try to get that toe track in the same scan. Looks like I need some more couplant. All right, there we go. So pause before it's all right. So the instrument is pausing. What I'll do, actually, I just realized I missed a lack of fusion. I want to show you this. All right, so let's get the track. This is the OD track. Let's refresh this. OD track. Then the root track, and we're moving towards the lack of fusion. There we go. All right, that's much better. Okay, I'm going to pause and show you the various displays here. So you can see this is a really live stream with all the technical difficulties associated to doing that in a webinar. So right now I'm in that live. I'm just paused, and I'm going to back up the scan position, the scan cursor, just to display that lack of fusion in the. Right now it's in the 4T mode. Now if I go to the next mode, this is 2T. Well, this illustrates very well that not all modes see the same defects. Some of them just don't see something as obvious as a lack of fusion. So the mode selection is very important for depending on what you're trying to find, of course. now I have this root track. Okay, it shows up on 3 modes but 1, and here we have the OD track or toe track. So the 5T particularly is quite interesting. It shows a profile, but the wrong selection. The 4T will also exhibit quite typical phase array signals using the TFM. So that was side and end view. I can also switch to top and end view. So each of these top views on the left. Okay, so the left pane is split in 4, so it corresponds to an actual top view showing all 3 defects. And still, I have 4 top views, and I do have a my end view that accounts for only for 1 mode at the time. Okay, so what I'm going to do is switch to a single layout that was multiple layout, and I have more options. This is one particular mode. Okay, so what I'm going to do is go to top, side, end, just to show you the layouts, various layouts applicable to multi-mode like this. So from there, you can actually screen, and review those indications. And you can obviously change mode, go to another mode for a specific purpose, whether it's for confirming something or it's for doing a screenshot that has more clarity. So all options are available. If I go back to my 4T that I quite like a lot, and I can display A end. So A stands for an A scan. Oops. Sorry, I should place my cursor before I switch. The cursor was off at the defect. I just want to show, say, something like this. Okay. Let's switch to A end. And now I have an A scan, which is a composite A scan, just being regenerated from the TFM reconstructed image. So I have the corresponding A scan with that data cursor. Okay, I hope you enjoy this portion. This was the first first section of this webinar, really centered on TFM. Now we're going to look into a little bit more elements, more on the phase array side. So the the OmniScan X3 on the current unit that I'm showing you right now, it's a 32-128 PR pulsar receiver that covers pretty much all of your PA-UT needs, I would assume. But it also features a handy 64-element TFM capability for when you need it. So if you have to use a larger aperture probe, a wider aperture with more elements, you can with this instrument while having all the convenience of a 32-128 PR for the general phase array. So number 2 message, improved phase array. So again, you may ask, why is that an improved phase array machine? So what makes it an improved? Well, one of the obvious is the specs. So as opposed to the previous generation, there's basically a factor of 2 between the maximum PRF you can obtain with a typical loaded layout. So maximum of 12 as opposed to 6 for an MX2. It also includes an improved TOFD experience. So I will not show you TOFD signals today. All I have on TOFD is the TOFD or time of flight diffraction, is that slide. But we've put efforts in simplifying the TOFD and simplifying the number of clicks it takes. Basically, we have this single menu that allows you to do everything you need to do with TOF, meaning calibrating wedge delay alone, wedge delay and PCS, setting up to 2 targets. So doing multi-group TOF becomes very handy with that menu. You have a calibrate button that is available online, meaning when the acquisition is running, or offline. So quite handy for the analysis as well. And that's not all. thanks to its state-of-the-art or high-quality electronics, we do have TOFD signals we're very proud of. So obviously that helps analysis when there's lesser electronic noise. So the OmniScan X3 is definitely capable of that and makes the TOFD experience quite simple. All right, moving on. OmniScan X3 is compatible with the scanners that Olympus supports. The scanners supported by Image2 are also supported by the X3. And that's also true for extensions and the splitters. The active splitters and extensions are fully supported. And probes, obviously, so you can, the equipment you already own will fit this instrument. I'm going to take you to a live demonstration on the phase array side, showing you a bit of the reasons why this is a better phase array machine. So you should see my screen here. Hopefully it's not too choppy. Again, the refresh rate is probably not as good over the internet than it is for what I have in front of me. This is the same configuration, by the way. I'm using the same probe. I have not changed the probe. I have not changed the blade. This is my same 40 millimeter, 40 millimeter thick weld carbon steel. I'm using my 5L32 A32 probe with the N55S angled wedge. And I'm just using the phase array engine of the instrument at the moment. So I will show you, this is a single group just to show you signals and basically show you the high quality and the sharpness of this instrument. Okay. So I do have this track here. What I'm going to do is zoom a little bit. Okay, so you can see a little bit better how the A-scan, how sharp the A-scan can be, and how clean the sectorial remains. So we used to have a video filter in the MH2. It's still there, only it's not turned on right now. So I can have that, powerful, clean S-scan, sectorial scan, without having the video filter on, so the A-scan will remain sharp. Now, I can turn it on to show you it's still there, so you can still use that if you like this feature. However, if you want to keep a sharp A-scan and see all the details from those tracks, you can. I mean, the OmniScan X3 has the capability, gives you the flexibility of using the most unprocessed signals to have a sharp A-scan there. Okay. Another feature we added to the S3 is, and I'm getting to it, is the high amplitude range. High amplitude range, basically up to a 800% dynamic range. Dynamic range, not dynamic range, but amplitude range. So if you think of it, you calibrate at 80% with a maximum of 800. So it's a total of a 10 to 1 on the dynamic range that you can obtain before saturation on larger defects like lack of fusion, for instance. So obviously, this is just for show. This is not a fully functional setup in the sense that it needs to be calibrated and so on. I just wanted to show you signals, but here I can, can demonstrate those various the sharpness of the A-scan while maintaining a very clean sectorial. So another thing we did on the X3, we implemented the onboard scan plan. For those familiar with Setup Builder, we reused in a way Setup Builder. We have put that in the instrument, and we have improved from it. So we have improved over it. I'll get to this section. But one of the improvements is making the interface very intuitive, but also allow some back and forth between your different tabs there. So 1 is the part and weld, 2 is the probes and wedges, 3 is the groups. So the user, you don't have to follow a specific sequence. You can go back and change something and then back again. Enables you to have a little bit more freedom on the definition of your setup, or if you forgot something, you can go back. You don't have to follow specific steps there. So this is my setup, okay, single V, and those are my weld parameters, my weld overlay. Again, the probe, showing you that it's the 5L32A32 probe. The bottom here, if you look for the index position, the index offset is located here. This one is the scan offset. So if you use a multiple group configuration, you will need to play with that. Let's say, for example, with TOFD, if you add TOFD or if you add a second pair of probes, you would need to play with the scan offset. Other than that, you have that index offset, and you can switch. You can toggle it. You can toggle sides like this, and create the setup very quickly. So let's go to groups. Groups. This is quite a loaded configuration with only one group. I just wanted to show you the, in a single screen what the F3 would be capable of. So I'm using 32 element, all my 32 element of the A32 probe in shear wave, and trying to cover as much as possible with only one sectorial. Just to show, this is just an example to show you how you would work with the this onboard scan plan. Now there's an other aspect I didn't touch is when I mentioned actually touched it briefly, but let's elaborate on it. We improved over setup builder in the sense that we added dual linear array, dual matrix array on board. We have onboard capability for these probes, and you would select them from there, from that menu. That basically allows you to do your entire setup on board without having to go outside from an advanced schedulator, from any other program and transfer files. These days are gone. So you can use the X3, do your setup, and go. That's all you need. All right. So I hope you enjoyed this portion. That's let me go back to the PowerPoint. Okay. Moving on into why this is a better phase array machine. Well, we also support legacy files, meaning that the MX2 files, setups, and data can be read on the OmniScan X3. Allows you to review your data over time or comply to older procedures. So, I'm sorry, I pressed the wrong button here. Apologies. All right. We also increased the file size. So the file size, basically, we wanted to make sure that you will not get stuck with a scan that you will have to cut in multiple sections and have to transfer and stitch afterwards. While this is still possible, the onboard file size has been increased drastically up to 25 gigabyte maximum, and you can actually send that to either the onboard disk, SSD, solid state drive, or you can use an external media and basically transfer it, not having to transfer it. You can save directly there. So how big is 25 gig? Well, three cases here. Say number one to the left, say you would use 4 TFM groups with optimized grid settings for the amplitude fidelity of 2 dB, and that would be up to 2 inches thickness, okay, 50 millimeters. Well, you could scan 10 meters in one scan. All right, another example, a little bit more stunning. It's possible, let's say you would define a configuration with a hydroform with a 1 millimeter by 1 millimeter pitch or grid. You would be able to scan a plate, an entire plate of 7.6 by 1.7 meters, which is what, 13 square meters in a single scan. Well, it's yet to see if anybody will be capable of scanning such along such a wide area in one pass without having other logistical problems, but actually the OmniScan can do it. So that's certainly not going to be your limiting factor. Another example real quick. So a loaded multi-group phased array configuration, 4 sector scans. Say you would want to do that. 2 linear and 2 TOFD. Well, that's a total of 8 groups. You could scan up to 20 meter in this diameter, so that's 65 feet diameter in a single pass. It's possible to go up to that level. Okay, transfer options. USB 3 is the fastest. SD card is still possible. I'll go quick on that. And that brings me to my last portion of this webinar with only so few minutes left. So I'll try to go a little bit more quickly for the time that's allowed to me. Thank you for those for anyone staying up to that point. So there's only a few slides left. So this OmniScan X3 enclosure is certified IP65, and that basically means it's rain and dust proof. Rain and dust proof, so it allows you to work in any harsh environment. It has a fan. We had to put a fan because when increasing performance, well, that heat needs to go out at some point. But the good news is the fan does not lead to the inside. It's only an external fan, so you can remove the fan yourself without having to send it back or having to open it. It prevents you from voiding your seal, your IP65, or your calibration. That's something that can be done in the field. Shall the fan becomes broken, of course. You can use, as we said before, you can use your existing batteries. Total duration between 4 and 6 hours. The ISO test gives it pretty much a little bit over 5 hours, and that's possible to do with 2 batteries. Of course, you can swap your batteries. They're hot swappable. You can leave one in, change one at the time, and the unit will keep working. Has onboard GPS that allows you to stamp the location on data files, so you can turn that on off. When you connect a wireless dongle, you can make that a connected instrument. The feature, at this present time, the only feature available through the Olympus Scientific Cloud is basically allowing you to download the latest software. And we do frequent updates, and we will keep doing that. So that's quite a handy feature. When you go back to the office with your X3, you can connect to the wireless and they download the latest software that's being populated there. So that brings me to my last live demo. I have a brief demonstration from the instrument and a little bit more. So as I was talking, I loaded a data file. Actually, this is on pause right now. This is the live feed from my instrument, but this is the phased array. It is a scan of the phased array configuration I was showing you earlier. Same probe. The only thing I did is I changed to an ABCS layout and I scanned the 2 defects that were on the same side. Okay. So what I want to show you, of course, we went through how simple the interface is. We went through the the various settings, how the menus are ordered in a way that new users will get used to it very quickly. Existing MH2 users will transit from it, and we'll see that it's quite similar. So I will not spend too much time on the menus there again. Just want to draw your attention maybe to the file menu that has moved to the section. Okay, enabling you to instantly access all of your most common functionalities you would need from the file menu without having to go back to the main menu there. So the rest is self-explanatory. You have groups and you have layouts. So I'm clicking on the buttons at the top, of course, and the last is the view. So readings, for instance, if I turn it off, it's the closest I can get to full screen. Okay, so the readings, you may notice there are 5. Okay, 1, 2, 3, 4, 5, and 5 more. So there are 2 pages for a total of 10 readings. And yes, you can still configure them. If you hold it, you can select reading list or select the individual reading. Now, what I'd like to show you is a little bit about the zoom. Okay, so we actually went quite quickly on that a little bit earlier. So let's zoom on that lack of fusion. So I'm going to press my my T-pad here, and there are two ways you can zoom. Either you click and it's concentric, or I'm going to do the other way, which is 2 clicks, and it goes by very fast. So we improve the zoom, or we fix the zoom, some may say, in order to make that a lot more handy and prevent false clicks and just extra steps. So the zoom is now a lot easier to use than it was. Let's enter an indication. So what I'm going to do is call my cursors, okay? And I will not try to have an exact, so anyone attending this webinar and watching me doing that will probably say he's not doing it the right way. I know it's on purpose. I want to just go fast and enter something in the indication table, okay? I know this is not the accurate way. I just want to box a defect and go to click the add indication, okay? And now if you look at the table, it says 1. So let's go in File menu, Indication Table Manager, and now we can actually do a little bit more. We can define the type. Okay, I have the type of, whoops, I'm sorry. I have the type of flaw. I'll call that as lack of sidewall fusion, and I can choose to reject it. So that's new. You still have your readings. Now you have a screenshot taken every time you do an actual, you enter an indication, and now you can export the table to CSV. So if you're using Excel after that, it's very convenient because you have your readings saved through a CSV, and you have your screenshot also available. Okay. So there's a last portion I want to show you with this live demo. It's the OmniPC. OmniPC is the PC version of the actual software, and it's a readback. It's an analysis program. So we've improved a couple of things on OmniPC. One of them is that we now can do we can open more than one file simultaneously in 2 instances, for instance. So you can have, right now I'm looking at the same weld, but looking at 2 indexes, one negative, one positive. So for instance, I could select a given position, note it's 6.4, okay? And let's say I want to review it from the other side, so I can load the other file. Let's go to scan, and let's go to 6.4, or I can use the cursor here, 6.4, and basically confirm what type of flaw. So that's one way how you could use it. Obviously, now I'm showing you only 2 files, 2 programs. If you have a larger setup with multiple computer screens, you could have multiple instances of OmniPC open at the same time. So we're almost at the end of this presentation. This is quite my last slide with 2 minutes left. Thank you again for staying that long with us and listening to this webinar. This is that slide almost is a reminder there are 3 models of the OmniScan X3 at the current time. There's a 1664 PR, more for manual corrosion applications. There's a 16128 PR for high productivity weld, normal thicknesses. And there's a 32128 PR for pretty much everything, including CRA, of course, higher productivity, thicker materials, even HTHA. So you have, depending on the range of product, you have the associated number of pulsars, 16 or 32. And keep in mind that the 16 element in phase array can do 32 in TFM, so the 32 in phase array can do 64 in TFM. The number of groups are not identical on all machines. The 1664 has only 2 groups, of course, has a lower price tag, and it can do a 2 PA and 1 Tuft or 2 TFM. So that was my last slide. Again, thank you very much to everybody for staying that long and watching this webinar. If you want to have more details on specifics of the OmniScan X3, please register to the webinar series that was announced. You will have a lot more details on individual topics. For more questions, you can ask your Olympus representative. And for those who ask questions during the webinar, since we're out of time, we will respond to them offline after the webinar, and we'll send those questions privately. All right. Thank you very much, everyone. Have a great day.
On behalf of Olympus, I'd like to thank all the attendees today for joining us, and Tommy for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. I'd like to thank you again for your interest and taking the time to attend our event, and we will see you again next time.